Hello and welcome again to my Physical Science online video lecture series. In today's video, I wanted to actually continue with the previous video from today, which was the Introduction to Thermodynamics topics for the physical science. In the previous video, I talked about heat and temperature. So in this one, I want to look a little more at the kinetic theory of gases, leading up to the ideal gas law. And so before I can do that, I wanted to give a quick primer on the phases of matter and specifically talk about gas in that context. So, there's many different possible phases of matter. There's sort of four phases of matter that are naturally very common. On Earth, the very common ones that we encounter are solid, liquid, and gas. There's a fourth phase, plasma, which we see on Earth in the form of like a lightning strike, but which is arguably the most common of these phases because it's the phase of matter that's found in stars. And there's other phases like the Bose-Einstein condensate and the supercritical fluids and so on. But I wanted to specifically contrast these other four phases of matter: solid, liquid, and gas. So with a solid, what you have is a object that's got a defined shape and volume. Basically, you're either going to have a crystalline solid, such as found in a mineral, where the molecules are basically arranged in this repeating pattern in like a crystal matrix. There's also amorphous solids like glass, in which the molecules kind of lack that ordered molecular structure. If you go to a slightly higher temperature with a given material, then it melts and you have a liquid. And what the liquid has is that the molecules are free to move around within the liquid, and so there's very little in the way of a lattice arrangement, anything like that. Liquids have definite shape, but not a definite volume. They have a definite volume, but not a definite shape. They lack certain properties of solids, such as that there is no, not any shearing to speak of. Like you can't really, with a solid, there's a shear modulus, and that goes away for liquids. You can't bend a liquid and have it bend back. And then as you go to higher temperatures still, the liquid vaporizes and you get a gas or vapor. And at this, when you're in the gas and vapor stage, then the molecules are basically no longer contained in any particular shape. They're not in a crystalline lattice. They're not even organized in the same amorphous state like in a glass. They're not just freely sliding across each other like in a liquid. Instead, they're free to move in any direction. They sort of bounce off of each other, bounce off the walls of the container, etc. And so in this gaseous state, your substance is going to have no particular size or shape, in as much as it can assume the size and shape of the container. And if the container has a variable size, for example, a balloon is a kind of container that can expand or contract, then you can determine what volume this gas is going to take based on an equilibrium condition. So more about that in a minute. The last one that I wanted to hit on before going into this kinetic theory of gases is the plasma. So that's at higher temperatures still. If you keep heating the gases, molecules start getting ripped apart, then the atoms start getting ripped apart in as much as the electrons start getting split off of their orbitals, and so you've ionized this gas. And so in this state, if all of the ions behave as sort of one fluid, and all the electrons that have been ripped off of the ions behave as sort of a second fluid, then you have basically a plasma. So on to the kinetic theory of gas, now that I've sort of said all that. So what do we have in a gas? Well, you have molecules that are all moving independently of each other. They're probably moving at high speeds. They're moving in all directions. And if they're inside a container, they tend to hit the walls of the container and bounce off. They also hit each other and bounce off. And so during these collisions, what happens? Well, you have a molecule moving at high speed. It hits the wall of the container and it deflects in some direction. So that means that the velocity has changed, because velocity depends on both speed and direction. So the direction changes, the speed may or may not change, but that does mean that the velocity has changed. If the velocity changed, that means that that particle accelerated, and if the particle accelerates, that means that some force has to be applied on the particle by the wall of the container or by other particles within the container. And by Newton's third law, that also means that these collisions involve the molecules applying some force to the walls of the container. And so how do we measure that force? Well, we've already talked about, in the context of my little peanut demo, this thing right here, we've talked about measuring the energy of the peanuts in the shaken peanut container, because that energy can be measured via temperature. Temperature is a measure of the average kinetic energy of the ensemble of peanuts. Well, there's another way, another kind of averaging that we can do, which is to find the average force that's being applied to the walls of the container. And the way that we find that average force is that we find the pressure that's exerted on the walls. So pressure is actually force per unit area. So that's the definition of pressure. So what it is that there's individual collisions happening pretty much all the time with the wall. And if you take all the collisions that happen to some section of the wall, you get enough collisions that there's an actual measurable force. And that measurable force is sort of spread over some area of the wall that gives you the pressure. So the units of pressure, by the way, are therefore newtons per square meter in the SI system, which gets the special name Pascal. There's actually several other ways to measure pressure, but two others that I wanted to mention. One is atmospheres. So 1 atmosphere is basically the pressure of our atmosphere on average at sea level at 0 degrees C. And it's approximately equal to 101,000 pascals, or 101 kilopascals. The other type of pressure is the U.S. customary unit, which is going to be units of force per units of area. That ends up looking like pounds per square inch. And so 1 atmosphere of pressure is actually 14.7 pounds per square inch. So notice that if you increase the force or you decrease the area, either one of those things tends to increase the pressure by definition. So in the context of gas, what causes the pressure to increase? Well, if you have more collisions, the pressure will increase. If you have a higher force exchange per collision, the pressure is going to tend to increase. Or if you have a smaller area over which those collisions are occurring, then the pressure is going to increase. So in terms of stuff we can measure, stuff that exists in this gas, what affects the pressure? Well, if there's more gas molecules, then there's going to tend to be more things to have collisions with, and therefore the pressure should increase. If there's a larger volume, then it means that the walls of the container are farther apart. It also means that the walls are larger. Both of those things tend to make collisions less frequent per unit area. So an increase in volume means a decrease in pressure. Last but not least, if you increase the energy of the molecules, mainly if you heat them, if you increase their temperature, then they're going faster, so that means less time between collisions, and also more force can be exchanged in a collision if the collision is like a ricochet, goes in, hits, bounces off at the same speed. You need more force to do that if the particle's moving faster. So to summarize what I've just said there, that means that the pressure is proportional to both the number of particles and the temperature, and it's inversely proportional to the volume. And it turns out that you can also reason through relationships like this for the number of particles. In other words, the larger the container, the more particles you can easily fit in at the same pressure. The higher the temperature, the fewer particles you can have in a container of the same size with the same volume, etc. And so if you put all these reasoned relationships together, what you end up with is that the pressure times the volume is proportional to the number of particles times the temperature. And the proportionality constant is that Boltzmann's constant that I introduced in the first part of this thermodynamics discussion. So actually the equation is that pressure times volume is Boltzmann's constant times the number of molecules times the temperature. And since Boltzmann's constant is used to convert from temperature to average energy, if you multiply the average energy by the number of things with that average energy, you get the total energy. And so the pressure times the volume tells you something about a total energy. Specifically, if you expand a container under constant pressure, you're doing some amount of work on that container. If you expand against a wall at constant pressure, then that change in volume times that pressure is actually an amount of work. So that is the ideal gas law. And to come full circle, I mentioned that the way you determine how large or how small a gas, how large or small a volume of gas is going to fill is that you use equilibrium. Well, basically, specifically, if you have something like a balloon, you put a gas inside the balloon and it expands out. There's actually a gas outside the balloon. The particles outside the balloon are colliding with the balloon walls, trying to push the balloon walls in. The particles inside are colliding with the balloon walls, trying to push the balloon walls out. And when the pressure outside and the pressure inside are equal, then you have an equilibrium condition. And so that's how that's what determines ultimately what volume that container will take up. If you have a rigid container that's sort of airtight, you put air in it, then the air will just fill that container up. There's not going to be much change in volume. If you have something like a balloon where the volume can change, well, volume will change to meet the equilibrium condition. So that's all for today, and thanks for watching.